Okay, as people are sitting, can you hear me back there? Okay. Now let's play this. Lights. Which one is better? Is better? No. Okay, let's converge to this. Okay, so welcome. Okay, just to remind you, this is the class. Unfortunately, there's only one screen. Hopefully, you can see it from everywhere. They promised me that eventually we'll get this back. I talked about this last time. You're going to see it at least one more time today. I want to remind you a couple of things. One is registration. Many of you have this question. I was wrong last time. The waiting list was much longer than I thought. So I'm not sure what's going to happen. One thing that I still request, if you decide at some point, or if you know that some of your friends that are registered and are not here plan to drop the class, please do it as soon as possible, because people really want to get into the class, and there's nothing we can do if people are not leaving the class. That's one. Two, people that are not registered and hope to be registered, don't worry. Everything is going to be open in this class, so we're not going to block things via Canvas. The lectures, the homework, the videos, once we figure out how to do it, it's going to be open, so you'll be able to access everything. Books. So the website is almost there. There's a lot of information. There's going to be a little bit more information about books. This class is not going to follow a textbook because I don't think there is a really good textbook for what we're going to cover here. We're going to be based on the lecture notes. There are books that cover partly the material. We're going to put pointers to it. They are all, and the list of what I think are the relevant books partly is already on the web. We're going to augment it a little bit. These are very expensive books. Don't buy them. Don't tell anyone I said so. I mean, if you are eventually going to do machine learning, you may want to have some of these books in your library, but for this class, it doesn't make sense to spend hundreds of dollars for this. All the material is going to be available, and if you really want to look at the books, it's available. All of them are available in the library also. So all the information is going to be on the website. We're going to correspond via Piazza. I know that many of you are already there. Please go on Piazza. As I said, Canvas is not going to be a limitation. One important thing, so what we are going to do is twice a week in the evening. The current plan is Tuesday and Wednesday. The information is on the website. We're going to have discussion sessions run by the TAs. This is in addition to office hours, the schedule of which is also on the web. We're going to start this Wednesday, which means tomorrow, with the first part of the Python tutorial. I assume that some of you are expert in Python, some are not. So I would suggest to come to the tutorial. And eventually, we're going to talk about other things that will prepare you for some of the material and talk about the problem sets, answer your questions, and so on. So that's this is going to happen in 3401, fourth floor. Just before you enter BC, there is an active learning room. The discussion sessions are going to be there. Questions? Okay, so okay, that's another comment that I made last time. I got a lot of emails, so you can still send me emails. Okay, so we're moving to what we talked about last time, the badges game. So let me remind you what it is. Don't give me the answer if you know the answer. I'm hoping that you know the answer. This is a real thing that happened. This is a 94 conference. I know that this is before many of you were born. This was one of my first conferences when I was a PhD student. There was a machine learning conference together with a learning theory conference, and you cannot see it, right? So when something like this happens, someone or all of you should say, we don't see anything. And then I'm going to try to do this and see if you can. Oh, wow. That's going to be hard. Oh, okay. Okay, you see something? Okay, you see the story. You can all go to the webpage and you see a few names. I'll show you slides for this. The key question, so what happened in this conference is that people, when they got the badges, as it works in conferences, had next to their name plus or minus, a label. And the organizer of the conference asked if people can figure out the rule behind the generation of this plus or minus. So this was a machine learning problem. A bunch of examples, all the attendees of the conference, small conference at that time, I think there were less than 300 or close to 300 people. Each one of them was an example, labeled example, plus or minus were the labels, and the question was, what is the rule behind this? And some of you figured out what the rule is, and so who knows what the rule is? Don't tell me the rule, just I want to show of hand. Okay, quite a few of you thought about it. All of you should have thought about it because it's a machine learning class, so you want to think about machine learning in your spare time. So people that know the rule, without telling me what the rule is, tell me why do you think you know the rule? Yes?
Because it fits all of the examples, and for there to be another rule that fits all of the examples that's independent from the one that I found means that the one that I found would have to be random chance, which is 1 over the 2 to the power of 294 chance, or roughly, which is really, really, really unlikely.
Okay, so you're saying that there is only one rule that fits the 294 examples?
I'm saying there could be other rules, but for there to be a rule that has nothing to do with the one that I found that fits everything, for there to be another one would mean that the rule that I found happened purely by chance. And for that to happen purely by chance is really unlikely.
Okay, so we'll revisit. This is an interesting argument. We'll revisit some of what you're saying here. Another reason, another argument that people are confident in the rule. Yeah? Repeatable, you means you can take the rule and evaluate it on other names, your own name, and you'll get plus or minus. Okay, and that's an important consideration because last time I showed you another rule that I'm sure is different than yours. This other rule was this list that I generated here. This is also a rule, right? It's a list of pluses and minuses associated with names, and it's completely consistent with the list. Probably not a good rule, but it's consistent. And it's different than yours, which will allow us to, or force us to think about what you're saying. Another argument. Yeah?
It's simple.
It's very simple. Why is that important?
With less moving parts, it's less complex, it's able to have less
That's actually very important. The reason is that, in fact, there's a huge number of rules that are consistent with this list. Huge number. You'll think about it a little bit now, and we'll get to it a little bit later today. Really a huge number. One of them is the list itself. It's consistent. Yours is another one. Maybe it's the same, maybe it's not the same. Huge number of rules consistent with these 294 examples. But most of them are not as simple. So simplicity is important because, as we'll see in the class, it will give us generalization. It will do well, or it has a chance to do well on example we haven't seen before. Okay, so let's see what we are doing now. Wow. Okay, sorry. Okay, so now that we have this, and you're sure that you got it, and you know why, let's look at it. So this is the data, or part of the data that you've seen. Now, what the people in the conference saw, they saw it a little bit differently. They saw these labels with names, and they were asked what function was used to assign these labels. Is your problem the same as their problem? In what way the problem I gave you and the problem they got are the same or different? Yes? Go ahead.
Do they have the entire list of names?
They got the entire list of names, or you got the entire list of names, and they saw people with badges. So that's one difference. Okay, another, yes?
They didn't know for sure if it was only the name itself that determined the function.
That's crucial, right? So I told you, by giving you this list, that it's in the name. I didn't tell you what's in the name, but they did not know that. It could have been the height, it could have been the shoe size, it could have been the country of origin, it could be many, many things. So your problems in this sense is much easier. And it's also much easier in the sense that I gave you all the data. They did not see all the data. So they got a list, and then they were supposed to make a guess on other people. So you can see my name there. You know, I'm a positive example. Lyle, for example, is a negative example here. So, and Shivani wasn't there, too young. What would be, people that know the truth, what would be the label of Shivani? Minus. Okay, so let's have it. What's the rule that you have? Give me the whole rule.
Okay, so,
If something happens, then it's a positive example.
so the second letter of the first name, if it's a vowel, then you'll have a positive. Otherwise, you'll have a negative.
So the second letter of the first name, if it's a vowel, it's a positive example. Otherwise, it's a negative example. Consistent with the data here? Everyone agrees that this makes sense, at least for these examples? Okay, so that brings a lot of questions. We asked the question of which problem was easier. There are really two options for a problem here. So one of them is, give me the rule, which is what you've done. The other problem, the other question I could have asked is, I don't care about the rule, just make predictions on other examples. It's not exactly the same thing. One of them entails the other, but not the other way around necessarily. The important question here is, what is the representation that you want to have of these instances? So I gave you a representation, a piece of paper with some characters on it. But what is the representation that you want to send to your learning algorithm so that there is a chance for us to induce this rule? Yeah?
Whether some letters are vowels or consonants.
Okay, whether some letters are vowels or consonants. So you say this because you've heard the hypothesis already. Before you heard what is the true hypothesis, would you take this as, would you say this is the first thing that comes to mind? What would you say then? Yeah?
Letter frequency.
What do you mean by letter frequency?
So the likelihood that a certain set of letters appear in a given name. So how often does A appear across all names, B, C, D?
But I don't need this data to determine how many times A appears in names.
But you want the data to try to find some kind of correlation between the information you have and the label.
Okay, so you want to know how often A occurs in positive example versus negative examples. Okay, yes?
The order of the letters in the name.
The order of the letter, how would you represent this?
You could just put them in a list or a vector or something, right? Just which letter comes first, which one comes second.
Okay, I probably want to be a little bit more concrete here. I'd like to say something like, this, I am the first character in the first name. I am the second character. I am the third. So, and so on. What other things do you want to know? Yeah? Length of the name, the length of the first name, the length of the middle name, the length of the last name.
Number of names, like it's three names versus
2 names, 3 names, 4 names. You can probably come up with a lot more. Now let's get to the question that you asked. What was the question that you asked in terms of representation?
whether the letter is a consonant or a vowel.
What is a vowel? I mean, it's not in the input that I gave you. Why don't you ask the question, do I have a letter that in the first name that the US president name starts with? Is it better or worse than a vowel? Or why don't you ask the question, is the first character in the first name one of X, C, D, F? Why is vowel better? Yeah? So it's some information that you brought from home. It has nothing to do with the data I gave you, and it helps you generate abstractions. It's not in the data. This is something that is important to realize. So really, there's some background knowledge that you brought with you. Now, if instead of the second character of the first name is a vowel, the rule that you would come up with is the third character of the first name is one of C, F, G, X. What would be with your simplicity argument? You would be less convinced that it's the true concept, more convinced that it's the true concept? Who would be more convinced? Who would be less convinced? Okay, so it's not as simple. One thing that makes it simple is that it involves some concept that you know exists and that serves here as kind of making this hypothesis more compact. So it's important. So you can ask the question, when did learning take place, really? The learning process of mapping this data into a concise rule, part of it happened after I gave you the data. You've never seen it before last Thursday. But part of it happened much earlier. where you learn some concepts, some abstractions, and you use them as a way to encode the representation, whether something is a vowel or not. And that's really important. And finally, algorithm. Any ideas of how would you take this data and write a program that will produce this rule? Or another alternative, take this data and write a program that, instead of produce this rule, what other alternative I could settle for? Suggestions? Yeah? Behave like this rule. Yeah, make the same prediction that this rule. So maybe I can represent this rule, second character in the first letter is a vowel. Maybe there are other ways to represent it, and my learning machine will produce another representation, but what I care about really is that it behaves the same thing, the same way, it makes the same prediction. So how would you do this? Any ideas for those of you that already know something? Yes?
You need to code the concept of vowel, remove, or not.
It's your program. So do whatever you want. But it's a good question. Ahead of time, I would suspect no one would have thought about vowels. Somehow, and I don't know how your brain works, you saw the light and you say, oh, vowel, makes sense here. As I said, if I would replace vowel but by a random set of 5 characters, I don't think you'll see the light. Maybe your programming, your machine learning algorithm will, but probably you won't, or it will take you a lot more time. Anyhow, so what we want to do is we want to be able to write a program. Most of you don't have an idea of how to write this program. By the end of the first problem set, you will. But the key thing I want to say now as we are moving is that it's really the same problem as the spam filtering that we talked about last time. It's really the problem of supervised learning where we're giving a bunch of data with labels, plus or minus, spam, not spam, and we want to be able to learn something, infer a program that predicts in a way that is pretty consistent with the data you've seen. So this is what we call supervised learning. So in supervised learning, we consider systems that apply a function, f, to input x and return some output y, which is f of x. So we have a collection of inputs. We're going to call them instance space in a second, x typically. We have a collection of outputs, which are our labels. In this case, we have 2 labels, plus or minus. And there is a system that computes, given x, f of x. Now, in supervised learning, we are not given f. Our goal is to look at a lot of examples, labeled examples, x, comma, y, and infer f of x. When do we do it? So this puzzle that I gave you is really just a puzzle. No one cares about it. We typically want to do it in cases where it's hard to write a program explicitly that looks at the x's and figures out and computes the y's. So spam filter is one example, right? So if I give you a few spam filters, a few email messages, whether they are annotated as spam or not, and you want to come up with a rule, a function that will predict accurately on the next email message whether it's going to be spam or not, it will be difficult. You cannot write a good rule that generalizes well, that does well on future emails. Similarly, I gave you this example last time. This is the short story that we talked about. In this short story, we also had these 3 names that are highlighted. Writing a conventional program that looks at Christopher Robin, Mr. Robin, Chris, and determines accurately, or many, many other examples like that, determine accurately whether these represent the same person or not, is very difficult. You don't know how to do it. No one knows how to do it. And we are writing machine learning programs. So we are allowing the program to read a lot of stories where we annotate it with these two names represent the same person, these two names do not represent the same person, and we hope for good. We hope that it will generalize. So that's the game we're playing. On the left side, we have input, X, an instance space, we call it. On the right side, we have a collection of labels. There is some function that maps X to the labels. We call it the target function, and our goal is to learn a model, another function, g of x, that is going to be as close as possible in a way that we'll define as we go to the target function. It's going to behave as close as we can to this target function. So in the middle, we're going to have this learning algorithm that is going to take training data, examples x, y's. They're going to be processed by the learning algorithm that will produce a new function, g of x. This is our predictor, this is our model. That's the game. And this is the game we've played before. Now you can ask yourself, are there other learning protocols? So this, I defined here a learning protocol. I gave you a batch collection of data, x1, y1, x2, y2, xn, yn, and you sent it to the learning algorithm. You could imagine other learning protocols. Suggestions? Yeah?
You can take one pair at a time and then slowly iterate and suggest different GFXs.
So this was the protocol that was used in the conference, right? So you looked at one person and you said, oh, okay, x, comma, plus. I wonder what that is. Invent a hypothesis. Let's go to the next person. Let's verify the hypothesis that we have on this second person's badge. Is it consistent with it or not? If it is, I'm happy. I'm taking my hypothesis, going to person number 3. If it's not consistent, I'm going to modify it. And then I'm going to go to person number 3. So this is more an online learning protocol. And you can imagine other learning protocols. We're going to discuss some of them in class. The key thing is that once you ran through this, you have g of x. You're done. G of x is the model that you're going to use in the world. This is going to be your spam filter. Now, in a machine learning class, in a machine learning environment, you're not going to be really satisfied with taking this g of x, be happy and go home, but you want to say, okay, is it good g of x? Is it bad g of x? You want to be able to test it. So the next step is we're going to test it. So we're going to assume that someone is giving us additional data, test data. It's also labeled. I'm denoting it here x prime, y prime. And we're not going to look at it together. We're going to look at the x's. We're going to run our model on the x's and see what we get. So we take our learn model, we run it, we get this g of xi's. We have the y primes, that is the gold data, the truth, and we're going to compare them somehow and get a measurement of how good our algorithm is. So this is what we're going to do in test. And again, we're going to discuss how to do it. There could be multiple metrics that we care about. You can also think about it, about can you use the test data that I've given you in other ways? Ideas, suggestions? What's the downside of what I did here? Yes?
By saying you use the test data in other ways, like what else can you use the test data for?
No, so what I did here is wasteful in some sense.
You're using some of your data.
Instead of training on the data that I had annotated, I wasted it, didn't show it to my learning algorithm, and used it for testing.
So you could, like after you create a learning algorithm, you could like predict on your test data and then feed that back into your learning algorithm.
I can do something like this. It could be risky because
Like you need your learning algorithm to be good in the first place. Right?
to do what?
You need your initial learning algorithm to be good on your training data before you can do that. Otherwise, like you're just gonna get wrong predictions in your GLX
right? So basically, I can be a little bit more clever about how I use the test data rather than waste it. There was another suggestion here, yes?
Can we introduce some noise to the test data and use it for predicting?
What will that give me if I introduce noise to the test data?
Initially, you can use the entire test data to find the model, and then you can have samples of the same test data by introducing some noise and use the second variant to.
So the risk in doing that, in taking the test data and training on it, is that I'm going to overfit the data, and then I will not know when I'm releasing the model to the wild, is it going to do well or not? That's the risk here. That's why we typically try to separate the test data. But one thing to keep in mind is that the test data can give you, even without labels, in some situation might give you some idea of what's the test data like. If you think about spam filters, maybe in the test data, all you see is messages from the same person somehow. Or all of them come within the same month. Or all of them are capitalized. You know, maybe the test data itself has some properties that you can somehow exploit. You learn something about the distribution of the test. Again, this is something that we may want to talk about a little bit later. So now that you have this notion of the supervised learning protocol, you can think about many examples. I'm giving you a few: disease diagnosis, part of speech tagging, given a sentence and determining what's a verb, what's a noun, what's an adjective, face recognition, given an image, name the person, name a property of them, are they laughing, is it a male, is it a female, automatic steering, you know, a component in automated driving. Many problems all fit into the same game. And in fact, if you think about it, a lot of problems do not look like classification problems, but really they are, or they can be decomposed to multiple classification problems. Example, automated steering. Another example, the story understanding problem that I gave you before. It consists of a lot of classification problems that interact. Okay, so with this in mind, we are almost done with the first bullet, the introduction, basic problems and questions. And I want to move into what are we really going to do? So what are the issues that we want to address in this class? There are really three types of issues. All of them are as important as others, but we're going to spend more time on the last one. So one of them is modeling. How do we take a problem and make it a learning problem? It's crucial because we need to decide how to represent the data. Think about the badges problem that I just gave you. If you, as a participant in the conference, would only focus on the person in front of you, their height, many visual properties of them, you would have no chance determining the rule. If you would focus only on their names, in this data that I gave you, you would have a chance. So the representation of the data is crucial. And of course, what is the learning protocol? Where is the data coming from? Where are the labels coming from? This is also important. So representation has two components. One of them is how to represent the data. The second component is what functions are you learning? You chose to learn a rule, a very simple rule. As I said, the same function can be represented using in other ways. Ideas? A function can be represented in many ways. So this was one function that says, if the second character of the first letter is a vowel, then say yes. Can you dream up another representation for the same rule? Yeah?
If the second letter of the first name is not a vowel, then say no.
Okay. But really it's the same representation, right? But I'm looking for really a different representation, yes?
Maybe if you gave like each letter in the alphabet a
Yeah, that's a great idea, right? So, in fact, I will give them because I'm going to write a program. So I'm going to index things and I'm going to code things. And you can probably write the same function as if the second position has this value, then say yes. Suggestion?
Yeah, I was gonna just say like combining the full name into one string and saying like character, percent character in the whole string.
Yeah, so that could also work. I was expecting some of you to say, use a neural network. It's a representation, and you can, if you encode the input in an appropriate way, a neural network will compute the same rule, but it will represent it in a very, very different way. Yes?
I mean, if you didn't get that the second letter should be a vowel, and you just thought about like sets of letters and matching, right? You have like, say a name has, I guess, 12 letters. Or no, I guess a name would have 20 letters, right? And you have, how many different sets can you make with 26 letters? You can make a lot of sets. So I don't really understand how, like, you know, if it isn't that simple rule, like your first premise, then you'll be really, you know, coding up like a rule like that would really, I mean, there'd be so many possibilities.
Yeah. So what you're saying, it's not as easy as it looks. And when you solve problem first one, and you use a learning algorithm to do it, maybe this will be the case. Okay, but my point here now, you should think about this. Representation is really important, both representation of the input, you could miss it altogether if you don't represent, if you don't attend to the right things, and representation of the functions. How is my G going to be expressed? And of course the algorithms, right? So eventually you want an algorithm that takes this input, produces this G, or produces, as we said, something that behaves like G. What are good algorithms? How do we define success of a learning algorithms? How do we know whether we are good on this data, but who knows what's going to happen in the future on data that we have never seen yet? We want to be able to get some guarantees. And of course, there's the computational problems. Most of you are computer scientists. There's an issue of efficiency or computational complexity. Can we even compute things efficiently? Or is everything we're going to do exponential, as you scared us? If we have to consider all the subsets of size 13 of the alphabet, it's a large number. We probably don't want to do that. Okay, so we talked about using supervised learning, and we have to account, and I want you to get used to the terminology because we're going to use it a lot. We have to figure out what is the instance space. So what kind of features are we using? Features could be things like the first character of the first letter is an A, the last character of the last name is a B, and so on. Or there is a vowel in the first name, or there is a vowel in the second place. What is our label space? What kind of learning task are we dealing with? What is the hypothesis space? This is the space of functions that our algorithm consider. What learning algorithms are we going to use? And how do we evaluate how good we are? So we're going to use the term loss function and evaluation metrics in order to talk about it. So instance space. So this is how we represent this X that we talked about, right? So designing an appropriate instance space is crucial. As our examples shown, we can think about Boolean features, which are most of the features that you've given me before. Things like, does the email contain the word money? Yes or no? Or you can think about real valued features. You can ask, how often does money occur in the email? You can ask, what's the width or the height of a bounding box in an image? What's the length of the first name? These are all features that you can think about. You can also think about, does the email contain the word money and the word send? Is this a different feature or conceptually different features than the one just above it? Does it end anything? Yeah?
If they're independent, then you could just make two separate features for money and send, but if there's some connection, like money might be normal if you're working in a job that has to do with money, but sending money might be more unusual, might be more expensive.
Okay, so I could have a feature, does sending money appear there? But here I could have, as you said, have a feature that says, is money in the document? Another feature is send in the document. Send and sending are not the same thing, by the way. Maybe you can abstract it so that they become the same thing, but at the text level, they are not the same thing, something to deal with. But let's deal with send and money. So I can have two distinct features. One asks for money, one asks for send, or I can have a feature that asks for the conjunction, both of them together. Is this the same or not? Do I add any information? Keep this in mind. It's an important question. We'll address it maybe even later today, and I'll ask this question again. Here are some features that we talked about already before, and once we have a collection of features, we can talk about the representation. So our instance space X is going to be a vector space. It's an n-dimensional vector space. N, capital N here, is the number of features that I have. Each dimension is going to be the feature. So each X is going to become a feature vector. And we can think about X as a point in some high-dimensional space. I don't know how to draw a high-dimensional space, so it's here a two-dimensional space. But in principle, you can already imagine that even in the case of the badges, which is really a toy problem, we are going to have a lot of features. If you care about the character and its position in the world, you will have a lot of Boolean features, right? Is A the first in the first letter? Is B the first character in the first name? Is C the first character in the first name, and so on? For the first location, you're going to have 26 Boolean variables. Same thing for the second, and so on. So you're going to have a lot of features if you want to encode things this way. So, and as I said, good features are essential. If you don't choose the right features, it's not going to work. We are not going to teach you what specific features to choose for the task. This is really a task-specific thing. We're going to try to talk a little bit about general principles here, but this is one of the key issues about machine learning. In fact, I would argue that 90% of the time people that do machine learning spend is on generating representations. 90% of the time CPUs work on machine learning problems. They work on the feature extraction problem, not so much on the learning algorithm. And you'll see that as you start playing with this. That was X. Y, what is the label space? We can, again, think about multiple label spaces. We can think about a categorical problem, binary classification, plus or minus. We can think about multi-class classification, K possible labels. Give me the topic of this news article. There are 20 possible topics: finance, banking, sports, politics, and so on. We can think about structured object in the output, right? So give me a sequence of labels. In the part of speech tagging problem, given a sentence, tell me which word is a noun, which is a verb, which is an adjective, and so on. It's a sequence. Maybe in some cases, I want to produce a tree in the output. Maybe in some cases, I want to be able to take an image and segment it to multiple regions. So again, it's a structure. It's an area that is called structured learning. We're not going to talk a lot about it. We can also think about labels that are real valued, regression. And I can also think about ranking, where my job is not to decide whether something is positive or negative, but my job is just to order X's, to say that X1 is more something than X2. I like x1 more than x2, or x1 is more about politics than x2 is about politics, and so on. So there are multiple problems. We are going to focus most of the class just on classification, either to Boolean values or to multi-class, or to do multi-class classification or real-valued functions. And the other question is the model. What is the function that we're going to learn? What is G? And in order to do this, we can start thinking about some real questions here. So let's look at this problem. This is your first real learning problem. The input contains only 4 features, not enough room on the slide, x1 up to x4. Let's think about them as Boolean features. So in the case of the badge problem, this could be, I care only about the first character of each name and the last character of each name, right? And I can ask the question, is the first character an A? Yes or no, this is x1. Is the last character an A? Yes or no, and so on. And so then I have a box that computes the unknown function, and it gives me the labels, f of x1, 2, 3, 4, 0 or 1, plus or minus. And here are examples. So I've given you 7 examples. If the input is 0, 0, 1, 0, it's a negative example. If the input, example number 3, is 0, 0, 1, 1, it's a positive example. Okay? So now, so that's the learning problem. Any questions? Clear? 7 examples with their labels. And the question is, can you learn the function? And if you can, what is the function? Yeah?
Is it x4 and not x2?
x4 and not x2. Let's check. So the suggestion here is x4 is on and x2 is off, then it's a positive example. Let's check. Does it make sense? So let's take example number 3. x4 is on, x2 is off, works. Same thing for 4. And these are the two positive examples that we have. Is it consistent with all the negative examples? Everyone agrees? Yes.
That's one rule. This, with this test data, could also be multiples of 3.
Say it again.
Multiples of 3.
What do you mean by multiples of 3?
So, number 3, if we look at this as a single 4-digit binary number, then example number 3 is actually the value 3, and example number 4 is the value 9.
Excellent. Are these two, any other suggestion? Yeah?
X4 and X1 or X3.
That's another function. Now, we got 3 functions. Are they the same function? Notice that a given function can be expressed multiple ways. So I'm asking you whether, let's take the first one, x4 and not x2, and the second one, multiples of 3, which is the first actually. I never got this as an answer for this. Is this the same function? No. What does it mean it's not the same function? Mathematically. Just tell me, yes?
There are inputs for which they would produce a different output.
Yeah. Important for you to say it explicitly. There is at least one input, a 4-bit sequence, on which your function and your function are going to produce different outputs. So what's going on here? So I gave you examples, I gave you a learning problem, and you produced 2 functions that are different, and both of them are satisfactory. So what's happening here? So let's look at it. So there are 4 bits, 4 inputs. How many? What is the size of my instance space? 16, right? 4 bits, Boolean, 16 input. How many different? And what I do here is I listed all the 16, and I put the label data on the 7 that I've given you, and question marks on the other 9. So the question you can ask here is, already you've given me 3 functions. How many functions are there over this instance space? Yes? 2 to the 9th. Why 2 to the 9th?
Because we know the result on 7 of them, right? So that means there's 9 unknowns, and there's 9 unknowns, and those can match either of 2 values.
So originally, if I don't have any labels, forget the y column here, there are 2 to the 16 different functions. Y 2 to the 16, for each y I can put either 0 or 1, and I have 16 options. So I can put 0 or 1 in the first place, 0 or 1 in the second place, and they're completely independent. So it's 2 times 2 times 2, 16 times. 2 to the 16, which is a large number, right? 65K is the number of functions. Now, I already fixed 7 of them. I gave you the labels, right? So that remains, and there are only 9 question marks here. So there are 2 to the 9 functions that are consistent with the data. 2 to the 9 is still a large number, 512. You only gave me 3. So there's more functions, 3 times more functions than people in this room that are consistent with the data. Each one of you could have given me 3 distinct functions, and everything would still be okay. So what's happening here? So that goes to your point at the beginning. You did the counting right, but actually there's a lot of functions that could be consistent with any piece of data that I give you. So what's going on, right? So we can figure out which of these 512 is the right one. What are we going to do? So the question you can ask yourself, is learning possible? What are we doing here, right? Because we have a lot of options. Each one of them, all of them are equally likely. There's no way, at least a priori, to prefer one of the other over the other. What are we doing here? Yes?
I mean, we did earlier, just like when we consider simple functions, so like maybe in conjunctive form or something like that.
So that's the only option we have, basically. So the only option we have is to invent this notion of hypothesis space and say, you know what? I'm not going to consider all 2 to the 16 function. I'm going to have some machinery or multiple options for machinery to actually restrict what I'm looking at. And this is going to be the hypothesis space. So in this specific case, right, as we said, I'm just summarizing the argument. There are y to the x size of label space to the size of instance space. In this case, 2 is the size of y. 16 is the size of the instance space functions, and the learner considers only a subset of the functions from x to y. This subset that the learner considers is the hypothesis space, is a space of functions that we allow, one way or another, the learner to consider. I could have said, as you suggested, let's just look at simple rules. This and this and this, just conjunctions. One second. xi and xj and xk, where I, j, and k range from 1 to 4 here. It turns out that this doesn't work. I'm not going to go over the details. You can try for each case here. I'm going to give you a counter example of why this isn't working. I could try other things. I could try, let's assume that I'm inventing the following rules. I'm going to say y is 1 if and only if at least m out of these n variables is on. Consider all the rules of this form and see if it's consistent with the data that I've given you. In this case, again, you can try it. It works. So the rule here, the rule here is 2 out of x1, x3, x4 is on. That's consistent. Notice that this is also different than the 3 options you've given me. It's another rule, but it's consistent with the data. And it's in my hypothesis space. So the key thing is that we found a consistent hypothesis, but we also have to think about the fact that you could have found something else had you started differently, had you considered a different hypothesis space. Question there.
Why can't we consider all the functions?
In principle, we can. it's going to be a huge space in general. Here we have just 4 bits. When we have a large space, we're going to consider, if we have 100 bits in the input, it's going to be much larger.
If we were to consider all functions, how would we make a prediction using all of them?
So the question first is, what will your algorithm do? How will you algorithmically search the space of all functions? Computationally, not going to be easy. You'll have to do something in order to do. Just think about the number of functions. 100 features. How many functions are there? 2 to the 2 to the 100. In a standard problem in computer vision, in natural language processing, the number of features is going to be 1 million. Not going to work. We have to think a little bit. And there are multiple strategies to do this, and I'm going to talk about it. So there are some learning paradigms that in principle could consider all functions. They don't really touch all functions, but in principle they could consider all functions. We're gonna get to it. But the important thing that I want to say here is that we have to make assumptions. In fact, I was expecting that someone will ask me, when will you get to neural networks already? So I was prepared to this, but no one asked the question. Nevertheless, don't worry, this function, and in fact all the functions that you've given me are neural networks or can be expressed also as neural networks. And we'll see this, so don't worry. Okay, so, but the discussion that we've had now proposes multiple views of machine learning. So what is machine learning? It's really the removal of the remaining uncertainty. Suppose we knew that the unknown function has a specific form, we're going to search only functions of these specific forms. Our problem is going to be easy. So in some sense, learning requires that we guess right. We guess a good hypothesis space. But of course, we could be wrong. And as we've seen here, we've given easily multiple options. All of them were good in one sense, but were different. So we could make errors. And we should be able, as part of our study of machine learning, also understand what assumptions we're making, what choices we want to make. How do we know whether we're good or not? So this gives us strategies, and I think this partly answers your question. So we can either work within flexible hypothesis spaces that in principle could express anything, all the space. Decision trees are like this. This is the first or the second real algorithm that we're going to talk about. Neural networks are like this. They're expressive functions. Now, even though they can express anything, algorithmically, we're going to make sure that we're not touching everything one way or another. Or we can say, you know what? I'm going to limit my expressive power. My G is not going to be anything. It's going to be some functional representation, like the functional representation that I've given you before. Out of n features, if m are on, say yes, and change n and m. This is a functional representation. Or I can give you some kind of a grammar, or I can give you a probabilistic representation of some sort, or I can give you a linear model. We're going to see what that means. So these are restricted collection of functions, still very large collections of functions, could be even infinite collection of functions, but still not all functions that one can define over a given input space. And our job is going to be, algorithmically, how do we work with this collection of functions? So eventually, once we make these decisions, our goal is going to be to develop algorithms either for the flexible hypothesis class or for the restricted hypothesis class. So let's start with a concrete example that I want to get to, and we'll address the modeling, the representation, and the learning within it. Here is one of my favorite examples, context-sensitive spelling. I don't know whether to laugh or cry. The prediction problem is given two options. in this case, whether type 1, whether type 2, determine which is the right one in the context of this sentence, right? So I'm showing you one example here. In principle, the data set is going to consist of a lot of text. The text will contain either the word weather type 1 or the word weather type 2 with the label that says this is the correct type of weather in this context or the incorrect type of weather. Everyone is agree with this? Is okay with this setting? So now we want to make this a learning problem. I want to look at a lot of data, and I want to be able to learn a model that is given a sentence with one of these weathers, and my model is going to say, yes, this is the correct spelling. No, you should have used the other weather. Okay? Learning problem is well defined. So the first question I'm going to ask is, given that my goal is to learn a mapping from a sentence to weather type 1 or weather type 2, really it's going to be sentences that contain either weather type 1 or weather type 2 to the right one. What is our domain? How do we define our instance space? How do we represent the sentences? Suggestions? Yeah?
One is like the Boolean features, so which is just which spelling it is.
So you're talking about the label, right? So whether the spelling is weather type 1 or weather type 2. But I need to represent the sentence itself because that's going to be the input to the learning algorithm, right? My assumption here is that what dictates whether it's weather type 1 or weather type 2 is the context in which weather appears. So I somehow need to give my program this information, right? So the question is, how do I represent it? Yeah.
Maybe like a vector of parts of speech,
Vector of part of speech, which means,
like noun, verb, something.
so first of all, when I read this sentence there, I don't see noun verbs written there. I see I, don't, know, whether. It's a good point though. I'm just trying to position it so that you will see that some information like vowels is not written. If you want to use it, you have to do something. So let's forget noun and verbs now, part of speech tags. Let's work with the raw data. Yes?
Yeah, I was going to say, like, some words can actually have multiple parts of speech, so you can't just map directly from words to parts of speech. For representation of the domain, you could probably do it just a list of words and then an index indicating where it fits in the sentence.
Okay, a list of words. So it's going to be a vector. What's going to be the first coordinate of the vector? I want to be more concrete. I agree with you. We want to represent words. You said two things. We want to represent words. We want to represent the location of the words in the sentence. Yes?
Also, we could use, I mean, just if you're asking what the instance space should be, a list of, or a set of English sentences that contain either the word weather or weather.
Yes, that's my instance space. Now, when I'm going to write a program, I need to encode this somehow, because when you and me look at it, we see a sentence. I don't know. We see something here. We probably see a lot more than what's written here. You see nouns and verbs, but it's not there. But you see it, right? So I need to encode it somehow so that I can give it to the program. By the way I'm going to encode it might lose a lot of the information. For example, maybe it will lose part of speech text that is something that you guys know, because I don't know why, and the program will not know. Yes?
So a sentence is like a sequence of words, right? And then there's always a certain sequence. So this whole issue of context always depends on where the word occurs in the sentence.
Or whether it occurs in the sentence. So we can have multiple granularities of context. But yes, you're right. So, but I want to get what is the first bit of the vector. Yeah.
So can we generate a dictionary and we encode each word that is possible? It's finite, and say like we encode I is 1, don't is 2. So and we have a fixed length of vector.
We can have a fixed length vector. What's going to be the length of the vector?
In the data we have, we can assign it as the longest.
The longest sentence. So what's going to be the first bit of...
First bit, if it is I, then the value is 1. If it is don't, the value is 2.
What if it's A?
And it's another number that we...
Okay, so what you have is a representation that is not Boolean. In the first coordinator, how many values will you take?
the size of the dictionary, I think.
The size of the dictionary in the first coordinate, the size of the dictionary in the second coordinate, and so on. Okay, that's a representation. I'm going to do something slightly different. I'm going to take, for each word W that I see, I'm going to define a Boolean feature that I'm going to call XW. Boolean feature, so it's 0 or 1. And XW is going to be 1 when W is in the sentence. Otherwise, it's 0. So in my representation, I'm going to have a vector of the size of all words in English. Let's say 50,000. Okay? In this sense, it's related to yours, but it's not the same thing because my vector is much longer. And I'm going to put 1. So basically, I have indices from 1 to 50,000. 1 is the word E. The second coordinate is the word B. The third coordinate is the word BE. The fourth coordinate is BEE, and so on. Order it any way you want. And then there's going to be 1 if the word appears in the sentence, 0 if the word does not appear in the sentence. So it's going to be a very sparse vector. In this case, 1, 2, 3, 4, 5, 6, 7, 8 words. So out of the 50,000 bits in my vector, 8 are going to be 1s, the rest are going to be 0. That's a sentence representation. Reasonable? Yes?
Instead of all the words in English language, can you make a space of all the words containing the letter W? Will have much less work to do?
Again, all the words that are?
All the words contain the letter W, so you have to source from less words.
Okay, all the words that contain the letter W, there's a suggestion here. Is this what I want or not? Yes?
Maybe instead just pull the words in your training set of data.
Okay, but let's, I want to think about this, all the words that contain W. Is this good or not? Why not?
We're concerned with the words that aren't whether, not the words that are whether.
Whether and whether are the label space that we have. These are the Y's. I care now about representing the X, and I care about all the words. In fact, you're right. I think we care really about potentially a small window around whether, right? So maybe I don't care about words if the sentence is 20 words long. Maybe I care about opening a window plus or minus 3 around my target whether, and I want to represent only those. Maybe I can do this. This will simplify my feature space a little bit. I can do other things. I lost some information in my encoding here. What did I lose? Yeah? I lost the order. You can add the order. If you think about how to add the order, instead of 50,000 dimensions, I'm going to get much higher dimensionality. Already, I have a lot of features. Almost any way you think about it, even in your representation, because you don't have a Boolean representation, you have a lot of values. Eventually, I want to translate it to Boolean representation. I'm going to get about the same thing. So there's no way around it. The dimensionality is high. If you wanted to think a little bit about who cares about high dimension, all we can see is 3 dimensions. This is why we care about high dimensions. Almost any representation of an interesting problem that you care about is going to be high dimension. So now that I did this, and I agree with you that there could be other representation, but this is one possible representation. We have time, right? Okay. Almost any representation will be something like this. So now we have a point in a 50,000 dimensional space. And in fact, we have two types of points. Some of the points are weather type 1 points, and some of the points are weather type 2 points. So this is, we've done the modeling step, right? We are thinking about the representation, but we haven't thought about the hypothesis space yet. Right? So far, what we have, and we also haven't talked about the learning protocol. So I want to ask a question about this. So how do I get data for this? Okay, let's skip this. Think about this at home. Maybe you can say, well, the professor gave me the data. But in this specific case, you can think also about, let's assume I want to solve this problem. I really want to solve the context-sensitive problem because Google Doc are lousy. They don't know how to do this. I want to learn a model. Where do I get training data for this? We'll talk about it at the beginning of next time. Now we want to take the 50,000 dimensional points that we have and put them there. So I put, this is a 50,000 dimensional space. Looks like 2 dimensions, but some of the points are purple points. Some of the points are red points. Weather type 1 and weather type 2. I put them there. And my goal is now to solve the learning problem, to find a function that separates the data. And there could be many functions. All right, so here is a function that separates the data. Right? It does a pretty good job. Here is another function that separates the data. Another one, another one. Which one do you like? Yeah?
Well, the first one, the squiggly one, it kind of violates the simplicity that we've been shooting for. So I would choose one of the linear ones, and it looks like the middle linear one has some schematic there.
Right, so the first one is doing the best job, but it's complex. In fact, you could argue, you know what, if you're allowing me to be as complex as I want, I can separate any data, right? But if you can separate any training data, what can you say about examples that will come up in the future? Probably not a lot. So that's really the idea of simplicity here. So I also prefer the linear one and probably the one in the middle because all the linear ones are making mistakes. I have some intuition that distances on this 50,000 dimensional space are meaningful, and therefore I'm going to choose the one that kind of minimizes something that makes sense to me. We'll have to make this a little bit more quantitative. So this is an important issue. This is about memorizing versus learning. The green one at the beginning really memorizes the data. But it's not clear whether it learns something, whether it's going to generalize. It's an important issue. What we're going to talk about next time is what's best and how to find it. So we're going to redefine the problem a little bit and develop an algorithm that will allow us to actually learn this for the first time. Final questions? Yeah.
Is the dimension of the space of the sentence space 50,000 to the 2, or that's just one word?
Okay, good question. So the dimension is 50,000, right? The number of instances in a Boolean space of dimension 50,000 is 2 to this, right? Because in each place, I can put 0 or 1. So the space is huge. The number of bit sequences of size 50,000 is 2 to the 50,000, huge. Now, the interesting thing, because we're talking text, most of them will never appear. No. So all I asked is, I put W there if it's in the sentence. If it appears 3 times in the sentence, I put it there once. If you want to account for repetitions, you'll define your feature space slightly differently. Final questions? Okay, see you Thursday. Tomorrow evening, follow the webpage and the Piazza. There is a tutorial, first tutorial on Python in 3401. Yeah, and you are giving it, right? Okay.
About like the representation,
Yes.
or like a binary representation versus word count, like how significant is it to keep in mind like the number of agreements?
In terms of quality,
Yeah, I guess if there's a way to say in general for natural language problems, whether it's just a value of words or like word count.
it depends. In most cases, in most interesting problem, in this specific